Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Vera Rubin's 1999 synthesis concerning the observational evidence for dark matter functions as a capstone document, a work of profound intellectual clarity, delivered at the culmination of a transformative era in astrophysics. It presents the accumulated wisdom of decades of meticulous observation, articulated with an authority that reshaped the modern cosmological landscape. This essay undertakes a rigorous evaluation of the internal claims, methodological assertions, and logical architecture of this pivotal work. By proceeding through a sequential analysis of its constituent arguments, we can illuminate the deliberative process by which a galactic anomaly became an accepted, if perplexing, cornerstone of cosmic reality. The analysis will focus exclusively on the specific assertions and chains of reasoning presented within the document itself, tracing the compelling narrative Rubin constructs from fundamental physical principles to the unavoidable postulation of a universe dominated by unseen mass. It is an exploration of a scientific argument in its most potent and persuasive form, one that defined the essential questions for the subsequent generation of physicists and astronomers. Section 1. The foundational problem of galactic mass and luminosity. The work commences by establishing a clean, powerful paradox at the heart of galactic dynamics. The introductory claims center on a fundamental discrepancy between two distinct methods of determining galactic mass. The first method involves a photometric approach. One measures the light emitted by a spiral galaxy and, using established mass-to-light ratios for known stellar populations and interstellar gas, calculates the total luminous mass. This represents the substance we can see, the matter that radiates. The second method is dynamical, deriving mass from the gravitational influence it exerts. The argument posits that within the framework of Newtonian gravity, which is presented as the operative set of rules for these scales, these two mass determinations should yield comparable results. Rubin's initial assertion is that they failed, so their divergence is both systematic and immense. The conceptual framework she details is elegant in its reliance on foundational physics. For an object in a stable circular orbit, the centripetal force required to keep it in motion, expressed as its mass times its velocity squared divided by its orbital radius, is provided by the gravitational force. This gravitational pull is proportional to the product of the object's mass and the total mass enclosed within its orbit, all divided by the radius squared. By equating these forces, one arrives at a direct relationship between orbital velocity and the enclosed mass. The paper's logic then unfolds if the majority of a galaxy's mass resides, with its luminous matter, concentrated toward the galactic center. Then for objects orbiting at great distances beyond this central bulge, the enclosed mass should approximate a constant value. Consequently, their orbital velocity should decrease in proportion to the inverse square root of their distance from the center. This expected behavior is what is known as a Keplerian decline. Rubin's primary claim in this section is the presentation of this Keplerian prediction as the unambiguous, accepted theoretical baseline against which all observation must be judged. The evaluation of this opening gamut reveals its strategic brilliance. By grounding the entire problem in first-year physics, Rubin makes the subsequent observational contradiction universally accessible and intellectually inescapable. The argument implicitly accepts the validity of Newtonian laws on kiloparsec scales. A crucial premise that channels the entire inquiry away from modifying gravity and toward postulating new forms of matter. Section 2. The spectroscopic technique for measuring galactic rotation. Having established the theoretical expectation, the work transitions to a meticulous exposition of the observational methodology. The central claim of this section is that long-slit optical spectroscopy provides a precise, reliable and high-resolution method for determining the rotation curves of spiral galaxies out to very large radial distances. Rubin details the specific technique, which hinges on measuring the Doppler shift of a particular spectral line, a hydrogen alpha emission line, With a rest wavelength of 656.3 nanometers, this line originates from clouds of ionized hydrogen, known as H2 regions, which are excited by hot, young stars and are plentiful in the disks of spiral galaxies. The methodology is described with compelling clarity. The slit of the spectrograph is carefully aligned along the major axis of a target galaxy. Light entering the slit is then dispersed by a grating, creating a spectrum for one side of the galaxy, which is rotating towards the observer. The hydrogen alpha line is shifted to shorter, BUA wavelengths for the opposite side. Rotating away, the line is shifted to longer, redder wavelengths. The magnitude of this observed wavelength shift relative to the line's rest wavelength directly yields the line-of-sight velocity of the gas at that specific point in the galaxy. By measuring this shift at numerous points along the spectrograph slit, from the galactic center to its faint outer edges, one can construct a detailed plot of rotational velocity as a function of radius. Rubin's argument for the superiority of this technique is a cornerstone of her evidentiary foundation. She presents the H2 regions as ideal test particles. Their intense brightness allows them to be observed far out in the galactic disk, well beyond the point where the starlight of the main disk has faded into obscurity. This allows the velocity measurements to probe the very regions where the Keplerian decline was predicted to be most apparent. The internal consistency of this section is formidable. It establishes the observational tool as a high-precision instrument, preemptively addressing potential critiques of methodological error. The choice of hydrogen alpha spectroscopy is framed as a deliberate and superior choice over earlier 21 cm radio observations of neutral hydrogen, affording greater spatial resolution within the inner regions of the galaxies and enabling a seamless tracing of the velocity profile across the entire optical disk. The claim is one of observational robustness, suggesting the data that follows are a direct and unmediated reflection of galactic reality. Section 3. The central evidentiary claim of asymptotically flat rotation curves. This section forms the empirical heart of the entire work, presenting the dispositive evidence that directly confronts the theoretical predictions laid out earlier. The principal claim is monumental and unequivocal for every spiral galaxy investigated. The rotational velocity, far from exhibiting a Keplerian decline, remains constant or even gently increases with distance from the galactic center. This phenomenon of asymptotically flat rotation curves is presented as a universal feature of spiral galaxies, observed across the full range of Hubble morphological types, from the tightly wound SAR galaxies to the more aplumbed SE types. The argument derives its immense power from the sheer weight and consistency of the presented evidence. The paper would here display a series of its no-conic graphs, plotting rotational velocity in kilometers per second against radial distance in kiloparsecs for a sample of galaxies. These visual aids are integral to the claim. The stark contrast between the gently falling dashed line of the Keplerian prediction and the stubbornly horizontal data points of the observed rotation curve creates an immediate and powerful cognitive dissonance. The work details specific examples, such as the Andromeda galaxy M31, where the velocity profile extends outwards, flat and unyielding, to enormous distances. By showcasing this pattern repeatedly across dozens of galaxies of varying size, mass, and luminosity, Rubin constructs an argument from induction. A single anomalous galaxy could be dismissed as a peculiarity. A systematic and universal behavior observed in every carefully studied object demands a fundamental revision of our understanding. The evaluation of this section's claims must focus on the universality argument. Rubin's research program, conducted with collaborator Kent Ford, was distinguished by its systematic nature. The paper leverages this by asserting that the flatness of the rotation curve is an intrinsic property of spiral galaxies. The data's internal coherence, with smooth curves and relatively small error bars, reinforces the conclusion presented in the previous section. The methodology is sound, and therefore the data are unimpeachable. The logical chain is simple and potent. If the velocity measurements are correct, Then the foundational assumptions about mass distribution must be incorrect. The flat curves are offered as direct empirical proof that the mass controlling galactic rotation is profoundly different from the mass associated with the stars and gas. Section 4. Proposing the dark matter halo as the causal mechanism. Following the presentation of the incontrovertible observational data, the work advances to its primary theoretical conclusion. The central claim of this section is that the observed flat rotation curves necessitate the existence of a vast, invisible halo of matter enveloping the visible galactic disk. This is presented not as a fanciful speculation but as a direct and unavoidable physical inference. The argument proceeds by returning to the foundational equation of orbital dynamics. The observation that the orbital velocity, v, is constant at large radii, r, has a direct mathematical implication, since velocity squared is proportional to the enclosed mass, m, divided by the radius for the velocity to remain constant as radius increasing. The enclosed mass must also increase in direct proportion to the This is the linchpin of the logical deduction. A galaxy whose mass is concentrated in its luminous centre cannot produce this effect. To satisfy the m proportional to relationship, matter must be distributed throughout a vast volume extending far beyond the visible disk. The work then deduces the required properties of this distribution. A spherical halo of matter whose density falls off with the inverse square of the radius would generate precisely the observed flat rotation curve. This dark matter halo is thus proposed as the causal agent responsible for the observed kinematics. In assessing this claim, one recognizes it as a powerful exercise in inference to the best explanation, presented with the force of a deductive proof. Rubin's argument meticulously constrains the problem. Having demonstrated that the luminous matter is insufficient, she introduces a new mass component whose properties are reverse engineered directly from the observational data. The claim is that this halo is the only viable solution that preserves the integrity of Newtonian gravitational theory. The work presents this conclusion as conservative, as it refrains from modifying the laws of physics and instead introduces a new, albeit unseen, physical entity. The argument's strength lies in its ability to explain the data perfectly with a single, coherent postulate. The dark matter halo resolves the mass discrepancy for every galaxy, and the universality of flat rotation curves implies a universality of these halos, making them a standard and fundamental component of galactic structure. Section 5. Speculations on the composition and implications of dark matter. In its concluding passages, the work moves from the certainties of astronomical observation to the more speculative realm of the composition of this newly inferred substance. The primary claim here is that the matter constituting these vast halos is of an exotic, unbaryonic nature. It is asserted to be a fundamentally new constituent of the cosmos, something distinct from the protons, neutrons, and electrons that comprise ordinary matter like stars, planets, and people. The argument supporting this claim draws from a different field of cosmology, Big Bang nucleosynthesis (BBN). The paper briefly alludes to the established BBN calculations, which successfully predict the observed cosmic abundances of light elements like hydrogen, helium, and lithium. These calculations place tight constraints on the total density of baryonic matter in the universe. Rubin's reasoning is that the amount of mass required for the dark matter halos, when extrapolated to the scale of the entire universe, vastly exceeds this baryonic budget. If dark matter were made of ordinary stuff, such as dim brown dwarfs, cold gas clouds, or stellar mass black holes, it would violate these well-tested cosmological constraints. Therefore, the argument concludes, the substance must be something else entirely. This claim represents a profound intellectual handoff from the domain of the astronomer to that of the particle physicist. The evaluation of this section shows Rubin defining the problem for the next scientific discipline. Her astronomical work established the existence and gravitational properties of dark matter. It is called meaning non-relativistic, dissipationless, and interacts with ordinary matter primarily, perhaps exclusively, through gravity. By framing the compositional problem in this way, Her work effectively provided the brief for the decades-long experimental search for candidate dark matter particles, such as weakly interacting massive particles WIMP or actions. The claim, while more speculative than the preceding observational assertions, is presented as the logical next step, the final piece in a puzzle that began with a simple anomaly in the rotation of Geller. Conclusion: Vera Rubin's 1999 synthesis on dark matter evidence stands as a monument to the power of meticulous observation married to lucid argumentation. The essay's evaluation of the work's internal claims demonstrates a masterful progression of scientific reasoning. It begins by framing a stark paradox rooted in classical physics, then establishes the unimpeachable credibility of its observational method. It proceeds to deliver the decisive blow with the universally observed phenomenon of flat rotation curves, a body of evidence so consistent and widespread that it commands acceptance. From this empirical foundation, the work logically deduces the necessary existence of a vast dark matter halo, reverse engineering its properties directly from the observed galactic kinematics. Finally, it extends the implications of this discovery into the realm of fundamental physics, arguing for the exotic, non-baryonic nature of this unseen mass. The intellectual architecture is seamless, guiding the reader from a simple question about galactic rotation to a paradigm-altering conclusion about the fundamental composition of the universe. The work's enduring significance, as revealed by this close analysis of its claims, is its role in cementing dark matter's place as a central, non-negotiable feature of the cosmos. It transformed a nagging anomaly into the dominant gravitational component of galaxies, providing the solid, observational bedrock upon which much of modern cosmology is built.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.